But to plot this resulting phase, I will use SymPy, and before plotting I will try to demonstrate that from this equation here we will get indeed the magnitude equals to 1 and the phase equals to this very complicated equation. So what I will do, I will use SymPy. So I'm importing here SymPy and the symbols, conjugate. This computes the phase, this computes the magnitude, this is the complex number, this is the exponential, this computes the conjugate of a complex number, and this is a SymPy plotting function. So here I'm defining the symbols I'm going to use. Here I'm defining first this equation given here. So this is here after some SymPy manipulation. So I am just doing exactly e to the power of minus j omega. So e to the power of minus j omega minus a conjugate divided by 1 minus a times e to the power of minus j omega. So this is exactly this, but SymPy has its way of already changing things. And then what I'm doing, I'm simply calling this ABS here that will compute the magnitude of this. The magnitude is given by this complicated thing, but when we replace a by 0.5, it will give us, this is what I'm doing here, I'm replacing a by 0.5 and it gives a magnitude equals to 1. And indeed, if I replace here instead of 0.5, if it's minus 0.5, and SymPy is taking some time to compute, but in fact it's also 1. So this is what I'm doing here. I'm replacing a by minus 0.5 from this equation here, and I am calculating the phase. So this is exactly what here. Here I'm using a equals to 0 and a equals to 0.5. So from omega going from 0 to pi, and this is the plot what we have here. So going back and recapitulating, I had this transfer function here with 1 pole and 1 0. I wanted to see that the magnitude is equal to 1, so I define this in SymPy. Then I call this ABS, which gives us the magnitude, and it gives magnitude equals to 1. So no matter what a we replace here, we will end up with the magnitude equals to 1. And I wanted to see this phase here. So what I do is I use this arg here. So if I apply arg to this transfer function here, and I replace a by, for example, minus 0.5, 0, and 0.5, we will get this plot here. And here we see the blue line is an all-pass phase for 0 equals to 0.5, the green line for a equals to minus 0.5, and the red line is for a equals to 0. And the phase is a pure one sample delay z minus 1 for when a equals to 0. So here we can be seeing that the beginning and the end of the curves are identical at frequency 0 and at frequency pi, but only in between the all-pass phase deviates from the one sample delay. So for a equals to 0, the all-pass becomes identical to z to the power of minus 1, which is a delay of one sample. So this is a pure one sample delay, and we can see that it behaves very similar to a delay. But we have, for different values of a, we have different characteristics And such an IIR Allpass can also be used to implement fractional delays. Okay? So in the above plot, we observe that we have different slopes or different derivatives of the phase function with respect to frequency, which shows different group delay for different values of A. So for instance, if we take the green curve, this is the green curve, is A is equal to minus 0.5. At the frequencies below half the Nyquist frequency, it has a slope which is about a third of the slope of the red curve, which is the delay sample one sample, and it represents a fractional delay. So this is A equals to 0. This is a pure one sample delay, but for example here we have different, these are our normalized frequencies and this is our phase. So this application is described in more detail, this splitting the unit delay article, the IEEE signal processing magazine, and you can download here and take a look to see how it's done.